Hi, and welcome to the EJC's online classroom. My name is Michael Wilson, but you can call me Professor, because I will be taking you through the land of physics. Now, I know some of you at home are wondering, oh my God, physics, the hardest subject on earth. Ye of little faith, physics is not. I assure you this is going to be a very, very smooth flight, and we will land at our destination safely. But before we get into it, let us pray. Heavenly Father, we come to you knowing that you are the all-knowing. You are the ultimate professor. You are the great teacher. We ask that as we go through this lesson that you electrify our minds, but more so electrify us so that we will be ready for your kingdom when you come. Be with us once more, we ask. Thank you for hearing our prayers. In Jesus' name, amen. Now we're going to be going into the topic of electricity, and we're going to be looking at electric current. And also explore the concept of Ohm's law and how we solve problems using this law. So let's get straight to it. Electric current. Now, in order for us to understand or to appreciate electricity to the point where we can even be grateful for this class, I want to introduce you to a very, very good friend of mine, Alessandro Volta. Now, I spent some time with this guy in high school, and you should spend some time with him as well, because we owe a lot to Alessandro Volta. Now, if we look at his name, we can realize that the electric quantity volt or voltage was actually named after him. Keep it on the slide for me. Right. So voltage was named after Alessandro Volta in honor of his contribution to the field of electricity. Now, why is this so? Alessandro Volta invented the first battery. Now, we all know what a battery is. It's the small unit that provides electrical power in a circuit. So this is what Alessandro Volta's battery looked like. Now, if you can see, there are metal plates lined in series on top of each other, but they are separated by a sheet of paper. If you look very closely, you see those white linings between the plates, and that is actually a sheet of paper that is soaked in salt water. Very interesting that Alessandro Volta could come up with such innovation. Now, the salt water actually acts as an electrolyte, which allows the passage of electric current to pass through and to power an entire circuit. Let's look at a simple diagram of this voltaic pile, as he called it. Now we see the orange layer, that's the copper metal, and there's a zinc layer on top, but in between we see the paper that is soaked in salt. Salt or diluted acid could work as an electrolyte. Any substance that creates ions basically can be used as an electrolyte. Now, what Alessandro Volta did actually, he would line the zinc and copper alternately to create a column to provide this electrical power called voltage. Now, I use the word power loosely, but forgive me for now. We're going to be getting to that concept in a while. Now, a battery is really a series of cells connected together, and a cell is just simply one single array of zinc and copper or any other two metal that are used. Now, Alessandro Volta explained to us that if the two same metals are used, then you will not get any voltage, any current to be flowing. So it has to be two different metals. So he used zinc and copper. You could use aluminum and gold. You could use graphite or any other conductor, as long as they are different and then of course separated by an electrolyte. In this case, Alessandro used salt water. So one single group or one single pair of zinc and copper is what we call a cell. Now when we put all those together, you get, voila, your battery. So we do owe a lot to Alessandro Volta. He also contributed to so many other things in life, the internal combustion engine versus driving cars. We owe this guy a lot. So I want to encourage you students to do some reading on your own about Alessandro Volta and his contribution to the field of electricity. But for now, let's move on. So what is electric current? Now I want to break this down in terms of concept. We're going to take the word electric and the word current, and we're going to separate them, break it down into simple concepts to come up with our definition. We're going to derive our own definition of electric current. So let's look at electric. Putting electric under the microscope, we know, or we should know, that electric, well, used in this context as an adjective, is having to do with charges or charged particles. Anything that is charged is described as electric, whether it be positively charged or negatively charged. We could even go further to even note that electric comes from or is related to the word electron. In this case, has a negative charge. So electric, having to do with charges or charged particle. Let's look at current. Now I researched the etymology of the word current, and it actually points to two words, running or flowing. And we might have heard the word current being used in different contexts, such as convectional current, which is basically the movement of air or water particles in a circular manner, or water current, which is the movement of water, whether it be a river or under the surface of the sea. Current, in this case, really has to do with a manner of flow. So electricity, or electric, is having to do with charges. Current having to do with flowing. So can we say then that electric charge, or electric current, is basically the flow of charge? Yes, we could actually do that. As a matter of fact, that is what electric current is. It is the flow of charge. But more specifically, we can define electric current as the rate at which charges flow through a surface. Now, that surface has to meet a certain condition, and we're going to get to that later. Electric current has an algebraic symbol, which is I. So when we're solving problems and we're working with current, we use the letter I to represent electric current. Now the measurement, or the unit of measurement of current, is the amperes, and we use the capital letter A to represent that unit. Now let's look at those conditions that I mentioned earlier that a material has to meet in order for there to be electric current, or in other words, a flow of charges. Now, these materials must be conductors. Here's why. What are conductors? What are insulators? Say, before I go to the definitions, conductors and insulators are basically direct opposite. An insulator is the opposite of a conductor. Vice versa. Conductor is a direct opposite of an insulator. Now, we're not talking about the men on the coaster bus loading and collecting fares, but we could use that in the context. But conductors in this case are materials that allow electric charges to flow freely. They are the green light of electric charges. So once the electric charges, when they are flowing, they meet up on a surface that are conductors, they only see green light and they go. Now these materials are such as copper, aluminum, zinc, most metals, and there are also other materials such as graphite and silicone. Some other, we call those semiconductors. But in this case, we're working with mostly metals. On the other hand, insulators, which I did mention, being the direct opposite of conductors, there would be materials that impede the flow of electric charges. they are the red lights. So when electric charges meet up on an insulator, they have to stop. They have no choice. It's a red light. They will be breaking the laws of physics, and trust me, the sanctions are very, 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 very high. So, what do we need for electric current? The material must be, which of these? Should it be a conductor or should it be an insulator? In order for there to be electric current, the material has to be a conductor. So in order for us to have electric current, we must use conductors. All right, so away with the insulators. Those insulators being paper, glass, plastic, and those kinds of materials. Materials that are pretty much not metals. Now, I might be putting myself into trouble here. Wait. Did I say paper is an insulator? Oops. This might be creating some disturbance in my brain-mind continuum. Why is it that paper is an insulator? But in Alessandro Volta's battery, he had a paper. Now, this calls for some thinking. Now, how is it that Alessandro Volta used a paper to separate those two metals, and electricity or electric current is allowed to pass across the paper? What is Mr. Wilson telling the students of Jamaica? That paper, being an insulator, allows electric current to pass through. Now let's go back to the battery. Now if we realize, even though paper is an insulator, Alessandro Volta did a brilliant thing by soaking the paper with an electrolyte. In this case, as we said before, is a salt water, or we could use dilute acid. So as long as there is an electrolyte present, then there will be some allowance of electric charges. We probably would say that there is a amber light in this case. We approach with caution, perhaps. So this is for you to think about now. I want you to research, how do electrolytes conduct electricity? Because we look at conductors being metals, pretty much solid objects. And we looked at insulators, solid objects again, plastic, paper, and all of those. And Alessandro soaked the paper in salt water. And that now allowed electricity to pass through. So your research is to find out, how does the electrolyte work? How does charges, how do charges pass through an electrolyte? Now you may do your research. You can do a presentation in the form of a project, and you can send it to my email. That will be given to you at the end of this lesson. So let's move on. All right, so while we sort out the difficulty that we're having here with the slides, the electrolyte, well, when you're doing your research about the electrolyte, you're going to be coming into some terms such as ions and cations and anions. Now, for those persons who do chemistry, they might have already been abreast or being au fait with these terms, or if you have not, then you will at some point in time go through the chemistry, I like to say the physics of chemistry, about the anions and the cations and the electrolytes, and you are required to do an experiment in this on electrolysis. I always tend to say that the there's only one science. Of course, in the words of Ernest Rutherford, that there's only one science. All the others are branches. Physics attempts to explain the others, or pretty much everything that we see around us. All right. So here we go. Moving right along. Great. Now, I want to introduce you to some quantities that are associated with electric current. Now, of course, we already know electric current. We've been talking about that from the beginning of the lesson. Of course, short for electric current, we just say current. And this, as we already covered, is the flow of charges through a conductor, specifically through a conductor. Current is measured in amperes. We also looked at that, and the symbol is I. Now, there's another quantity that I want us to look at. Now, I've made mention about it when I introduced it to my friend, Alessandro Volta. Voltage was basically given to another electrical quantity in his honor, measured, of course, in volts, and that is the electric pressure that causes the current to flow. Now, I want us to pay attention to the difference in the definition of these terms. The current is the flow of charges. However, voltage is the pressure, or the electric pressure, as it were, that causes the current to flow. So it's almost like the charges are vehicles, but the vehicles need a force to push them to move, which would be the engine. And of course, the engine being the battery that provides the voltage. So as long as there's a battery in the circuit, then there will be current. There's no battery, no voltage, no pressure, no electric pressure, no flow. The other electrical quantity that I want us to be familiar with is resistance. Now, we have to talk about this because it is in our reality. We experience resistance in every movement that we make. Most common one is friction. Now, in the field of electricity, friction in this case is called resistance. And this is the hindrance to the flow of charges. So while current might be flowing because of the electric pressure given by the voltage, there is resistance in some way that the charges are experiencing in the circuit. And we're going to be looking at how these are related to each other. In other words, we're going to be looking at a law. But before we do that, let's just summarize what we just did a while ago in terms of the is associated with electric current. Of course, we know current, electric current, short for current, having an algebraic symbol I, measured using the unit amperes, unit symbol capital A. It's very important that we take note of these because when we are solving problems and we're writing our values, we must use our proper units. Voltage, algebraic symbol V, unit symbol, of course the unit is volt, and so the unit symbol is volt. I love to say this, I cannot say it too much, that my dear friend deserves this honor, Alessandro Volta. Now, resistance was really further discovered by another scientist having the name Ohm, and so the symbol is given in his honor. Resistance uses the algebraic symbol using the unit Ohm, which has a symbol represented by the Greek letter omega. Now, I don't want you to be confused because omega is used to represent a lot of other quantities, but in this case, once we're dealing with electricity and you see the horseshoe symbol, which is the omega, the Greek letter omega, then we're talking about resistance. So how do these three quantities relate? The answer to that is Ohm's law. Now, in physics, we will be presented with many laws that govern how we calculate and how we deal with problems on a day-to-day basis. So in this case, we're going to be looking at Ohm's law. So let's get straight to it. What does Ohm's law say to us? Now, Ohm's law states that the voltage between 2 points in a circuit is directly proportional to the current through those points. So we have a voltage, which is the pressure providing the current. That voltage is directly proportional to the current that the voltage causes in the first place. Makes sense? The more the pressure, the greater the flow. So the higher the voltage, the higher the current. Let's get back to it. Now, this is a mathematical representation of Ohm's law, which simply says what is stated in words. V, as we know, is voltage, and I is current. Now, that symbol in between is another Greek letter, alpha, and it symbolizes, or it means, is directly proportional to. So, that short mathematical statement is read. Voltage is directly proportional to current. Now, if you have done variations in your mathematics course, then you should know what direct proportionality or direct relation means. Let's go back to it. Now, if V is directly proportional to I, it means then that a ratio of V against I will give a constant K. Now, if you haven't done this yet in your mathematics course, trust me, you will be introduced to it in time. But just a simple concept, if V is directly proportional to I, then V divided by I will give a constant K. Let's go outside the box a little bit, just for this concept to come home to us. Donkey and cow. Let's say donkey is directly proportional to cow. Then donkey divided by cow will give a constant K. It simply means that however one variable increases, the other will also increase, such that the ratio between the two never changes, which is why it is called a constant. Now let's get back to it. The constant K in the field of mathematics, and of course field of science overall, is called the constant of proportionality. Now, various experiments carried out yields that this constant of proportionality happens to be the resistance in the circuit. So basically, voltage and current are directly related such that their ratio always gives the resistance in the circuit. Now, by virtue of transposition, we could write, making V the subject of this formula, voltage is equal to current times resistance, or V is equal to I times R. To remember this, we could say there is victory in resurrection, or victory in redemption. For short, victory in redemption, for short. But always remember, V is equal to I times R. Voltage is equal to current times resistance. Now we need this equation for the next problem that we're going to be looking at. Now, first example that we're going to be taking a look at is a circuit having a current of 3 amperes and it experiences a resistance of 4 ohms. What is the voltage? Now let's get back to the law. When we're solving problems, we have to identify our known values and our unknown values. So what are our known values? Now, based on the problem, we know the current. The current is 3 amperes. We also know the resistance, and that is 4 ohms. What we do not know is the voltage. Now, from the law that we've looked at, Ohm's law, we know that V is equal to I times R. We know I and we know R, but we don't know V. So this equation is already set for us to determine the value of V. So we say V is equal to something times something. Going back to the problem, of course, we identified that current is 3 amperes, resistance is 4 ohms. And so voltage in this case would be equal to 3 times 4. You don't need a calculator for this one. 3 times 4 is 12, and so the voltage across this circuit is 12 volts. Let's take a look at another problem. Before I go, let me give you some time for this to soak in. So, we said that the current is 3 amperes. And the resistance is 4 ohms. We needed to find the voltage. Identifying that the current is 3 amps, the resistance is 4 ohms, V is equal to I times R, therefore V is equal to 3, because the current is 3 amperes, times 4, because the resistance is 4 ohms. And therefore, 3 amperes times 4 ohms will give us 12 volts. I believe this is good for us. We can move on to the next problem. So we've looked at a problem where we know the current and we know the resistance, but we need to find the voltage. Now this time we're going to switch things up a bit. Let's look at this one. The voltage drop across a lamp in a circuit is measured to be 0.42 volts. If the current passing through the lamp is 0.21 amperes, what is the resistance of the lamp? So in this case, we know the current. The current is 0.21 amperes. And we also know the voltage, which is 0.42 volts. What we don't know is the resistance. So remember, we have to use Ohm's law. What does Ohm's law say? Ohm's law says that voltage is equal to current times resistance. Now we want to find R, the resistance. So we need to shuffle this equation or transpose, in the words of mathematics, to make R the subject. And of course, this is pretty much where we came from in the first place when we were dissecting Ohm's law, that V over I is equal to the constant R. And so R is equal to V divided by I. So therefore, we can say that R is equal to something divided by something. Since V is in the numerator, then we would put 0.42 in the numerator and I in the denominator being 0.21. Now we should need a calculator to do this one as well, because we should realize that these two values they have common multiples, and so 42 divided by 0.42 divided by 0.21 will give us 2. We could look at it as 42 divided by 21, and it would make it a little easier to realize that the common factor here is 2. The common multiple is 2. Alright, so let's recap this problem. So the voltage was given to be 0.42, current 0.21. And we were asked to find the resistance. Resistance is the ratio of the voltage and current. And so it is given as voltage divided by current, according to Ohm's law. Now, since the voltage is 0.42 and the current is 0.21, then resistance will give us 0.42 divided by 0.21. And that is 2 ohms. Now I want us to note that whenever the final result or the final result is given, yes, the final result, it is always given with the unit. In the previous problem, we were asked to find voltage, and that voltage was worked out to be 12 volts. And so we wrote V equals 12, and we put the unit sign, which is V, in the case of voltage. Now in this case, we were asked to find resistance. And so we were careful to write 2 ohms. Remember that the symbol for ohms is the Greek letter omega. So we write 2 omega. However, it should read 2 ohms. All right? Now, if the statement is written R equal 2, then that is entirely wrong. Because 2 by itself can mean anything. Could be 2 horses, 2 donkeys, 2 cows. So we have to put the unit. Since we're talking about resistance, then we will say R equals 2 ohms. It is very important. Now let's move on to a third problem. We've looked at a problem where we know the current and we know the resistance. We're asked to find V. We're asked to find voltage. We also looked at a problem where we know the voltage and we know the current, but we're asked to find the resistance. In this case, it's different. This problem gives us a voltage drop across a 6 ohm resistor measured to be 0.5 volts. What is the current passing through the resistor? Now our known values in this case are resistance, which is 6 ohms, 6.0, same as 6 ohms. Now I write 6.0 because of consistency. Since the next quantity is given in 1 decimal place, then I write my 6 ohms to 1 decimal place as well. So I write it as 6.0 ohms and I write voltage 0.5 ohm for the purpose of consistency. Now in this case we want to find I. Always remember your Ohm's law equation. V is equal to I times R. Now since we want to find I, we make I the subject of the formula by virtue of transposition. So we yield I equals to V divided by R. And so, in order to find the value of I, we know that it is something divided by something. Since we know the voltage to be 0.5, that goes in the numerator because V is in the numerator, and R being 6.0, that goes in the denominator. And so I is calculated as 0.5 divided by 6.0, and that yields 0.08 amperes. Now, Ohm's law is very, very, very useful, especially when we're dealing with circuits designed. Those persons, those electrical engineers, need to know Ohm's law, and we have to give thanks for them, because if had it not been for electrical engineers and electronics engineers, then we wouldn't even be having this class today. And so that is why I have to pay homage to Alessandro Volta, who came up with the battery. Now, in other lessons to come, we're going to be looking at circuit components and the arrangement and the design of circuits, and other calculations such as effective resistance and so forth. I just wanted to introduce you today to Ohm's law and how to calculate the values using the relationship given by Ohm's law among the volt, current, and amperes. Of course, there are other electrical quantities for us to familiarize ourselves with. Those are power, capacitance, and so forth. However, we're just looking at current, voltage, and resistance for today. Now, it's very simple. Going back to the problems that we solve, of course, remembering our Ohm's law equation, V is equal to I times R, then we can solve any problem involving current, resistance, and voltage. Of course, using Ohm's law. Now, can you remember what Ohm's law states? Now, if you don't remember, let me remind you. Ohm's law states that the voltage, between 2 points in a circuit is directly proportional to the current through those points. And remember that proportionality means that the ratio between those two values gives a constant. That constant being resistance. Now, when you're doing an exam, there might be a question that will ask you to state Ohm's law. So this is just for you to remember. However, it is very important also that you explore Ohm's law a little bit more, and of course the concept of direct proportionality, because Ohm's law is not the only law that speaks about proportionality. And so the more we understand about direct proportionality, and even more so inverse proportionality, then it gives us more ability to solve problems involving proportional relationships. Of course, there's also graphs to be drawn that represents certain types of relations, such as direct proportionality. All right, so let's say voltage is directly proportional to current. How would a graph look for voltage being directly proportional to current? Sorry. Go to the board a little. All right, now since voltage is being measured against axis, I hope you can see clear enough. So we have a graph, current. Alright, so I still use my algebraic symbols, voltage being V and current being I. If voltage is directly proportional to current, the graph must give, if voltage is directly proportional to current, then the graph must yield a straight line passing through the origin. Drawing with my look like this. If the graph doesn't yield a straight line, then it does not represent a direct proportionality. Now, when we find the gradient of this line, since the constant of proportionality is the resistance, then the gradient, which would be the change in voltage here over the change in current, must give us R. So a graph of voltage against current will give a straight line passing through the origin, and this is the origin here where both values are 0. Now, if voltage is directly proportional to 0, when voltage is 0, then the current must also be 0. So that is why the graph must pass through this point called the origin. Now, if voltage increases, then the current must also increase in a way that the rise is always a constant, or even if there is a decline, it's a constant decline. And so the gradient, of course, would be worked out to be the constant of proportionality, which in this case is the resistance. All right, so if cow is directly proportional to cat, then a graph of cow against cat must yield a straight line graph passing through the origin. And the constant of proportionality would be the gradient of that graph. So that's pretty much the concept of direct proportionality and direct relations. So Ohm's law speaks about direct proportionality, giving a straight line graph passing through the origin. Now, it's sufficing to say that plotting a graph of voltage against current is another way of solving problems involving voltage and current and resistance. So you might be given a series or a group of values for voltage and a group of values for current, and we plot those values on the graph. We should yield a straight line, and of course, to determine the resistance, we simply determine the gradient of the graph. Simple. So for those persons who are saying that physics is the hardest subject on earth, it is not. All right, Professor Wilson is here with you. And if you have any questions, my email address will be given at the end of this lesson. Let's move back to the slide. I want to give you, the students, a chance to attempt a CXC or exam type question. All right, let me jump to that slide quickly. All right, so while I'm getting to that slide, now when you're answering exam type question, it's very important for you to take note of the question itself. Now sometimes answering exam type question is not about what is required, but is how we interpret the question now. Can we go to the slide? All right. So I want you, students at home, to attempt this question. A 12-volt battery is connected to a circuit with a variable resistor, and an ammeter is used to measure the current in the circuit. The first question should be easy, but I slipped in the second one to toggle your minds a little bit. So I'm going to give you some time to do this. Now, what I would love if students at home can do this problem, maybe take a picture and send it to me so I can see that that you are all learning, or you all have learned. So while you're looking at that question, let me recap. What have we done today? Now we've looked at the concept of electric current, and we spoke about Alessandro Volta, the genius who contributed greatly to the field of electricity and electric current. Of course, creating what we now call the battery. In his days, he called it the voltaic pile. Simply being an array of metal plates, zinc and copper, one above the other, separated by a piece of paper called an electrolyte card, soaked in electrolyte, which is salt water. Now, if you want to create your own voltaic pile, you can do that at home. You can get your metal plates of different kind. It could be a zinc and copper. It can't be the same. All right, so you have to get two different types of metal and a sheet of paper. It could be a cloth, and you soak it in salt water or dilute acid. You could use vinegar and try to light a bulb. All right, there are a lot of experiments on the internet that we can watch that demonstrate this kind of phenomenon. Now, we also looked at the concept of electric current. Current being a flow and electric having to do with charges. And so electric current we deduced to define as the flow of charges. More specifically, the rate at which charges flow through a conductor. All right, remember that in order for electric current to exist, there has to be a conductor. So charges only flow through a conductor. All right, and remember your assignment, of course, about how electrolytes allow electric current to flow, being as the material used is an insulator. However, it is soaked in an electrolyte. Now, you were also introduced to three basic quantities of electricity: current, voltage, and resistance. And we explored the relationship among these three variables in the concept of Ohm's law, which states that the voltage across 2 points in a circuit is directly proportional to the current. The constant of proportionality in this case is resistance. Remember your Ohm's law equation, V equals I times R. Of course, there is victory in redemption. And of course, there's also victory in the resurrection. So that could be used to remember V equals I times R. Now we've used that to explore a few problems. One where we know the current and the resistance and we're asked to find the voltage, or where we know the voltage and the current and we're asked to find the resistance, or we know the voltage and the resistance and we're asked to find the current. Now note that in any case you must know two variables and ask to find one. There's no way you can find two unknowns with one equation. It's not possible. Your math teacher will tell you that you will need a simultaneous equation for that. And that is a topic for another time. As a matter of fact, that is a mathematics class. Now, if you tune in to the next class, then we just might be lucky enough to learn a little about simultaneous equation. All right? So you must know two variables and ask to find one. So we looked at three cases. Two variables that are known, one variable that is unknown, and we use the equation V equals I times R to determine the unknown value. Now, I'm sure by now you must have finished your exam type question. And so I'm going to use the time now to wrap up and to tell you thank you very much. My name is Michael Wilson, but you will call me Professor. And that was our physics class for today. My email address is professorwilson2015@gmail.com. I am so eager to see your emails. If you have any queries, feel free to send me an email, and I will be sure to respond. Thank you.